So today we're going to be looking at a phenomena called diffraction, and diffraction can happen to any kind of wave. So what is it? So let's say I had these waves coming along here and their wavelength was, let's say, lambda. Now I have this gap here, and let's say this gap is the distance of that gap, or the separation of that gap, is roughly equal to lambda. It's around the same order of magnitude. And as these waves pass through the gap, they will start to bend. And this phenomena is what is known as diffraction. Now, if I decided to make that gap a bit wider, what you will see is that the waves will bend, but they won't bend as much as if they would if the gap was narrower. If the gap is wider, there is less diffraction. And you may have noticed this sort of phenomena when you're maybe at the beach or the seaside and you can see a wave passing through, let's say, two cliffs. So let's say I have this laser of red light, and we are told two things about this laser. We're told that the light coming from it is both monochromatic and it is a coherent source. These are two definitions that you should be really comfortable with when you're going to your exam. So what do they mean? Well, monochromatic simply means that the light source is of a single frequency or wavelength. So in this case, there's only one wavelength of light being emitted by this source. It will be the wavelength of red light. And lasers are pretty much always monochromatic sources. Now, what a coherent source is a source that is both monochromatic, i.e., it forms two waves that have the same wavelength or frequency. But the most important thing is that the waves maintain a constant phase difference. This is what the examiner will be looking for in particular when talking about coherent sources. This means that two waves emitted by the source will have the same phase difference. That means they can have the phase difference of pi, 2 pi, 27 degrees. It doesn't matter as long as it's the same phase difference throughout. So what happens with this red light? So we're going to emit wave fronts, and the distance between these wave fronts is obviously lambda. And what's going to happen is it's going to pass through this gap. And we're going to call this gap a single slit. This is something known as the single slit experiment. So this wave, as we know, is going to start bending or diffracting after it leaves this gap. So what goes on? Well, when waves meet, or you could say superimpose, in phase, so that means that they have a phase difference of 2 pi radians, they will constructively interfere to form maxima. And the opposite goes for when they meet in antiphase. So that means it's a phase difference of pi. They destructively interfere to form minima. So what would we observe? So let's say I put a screen here. We know that when the phase difference is 2 pi radians, or the path difference is n lambda, a whole number of wavelengths, it's going to form a maxima. So let's say here is a 0 lambda position, here's a 1 lambda, 2 lambda, and the same here, 1 lambda, 2 lambda. We know that here there are going to be points of maximum, and the opposite goes for path difference of half lambda. So at every half lambda, you're going to see minima. So therefore we can kind of guess that, well, this wave is going to look something like this. So it's going to have minimum amplitude at these points of minimum, and it will have a maximum at places where the path difference is a whole number of wavelengths. But as we get further away from the center, it's starting to get further away from where the peak of this wave is. We can see that here there's a peak in this wave. So as we get further and further away from the center, we're going to actually start to see decreasing maxima. So we'll start to look something like this. So what you can see here is you'll see a very bright central maximum. And you'll see decreasing maxima either side of that central maximum. So let's go and determine where we're going to find these points of maxima on this diffraction pattern. So for a single slit diffraction pattern, we know it looks something like this. We can see that here are the points of maxima. There'll obviously be one maxima right in the center, and other two at some angles that we are unsure of. So how would we work out these angles? So let's call the angle between the central maxima and one of these maxima theta. Now this angle is dependent on a few factors. It's dependent on the wavelength of this light and the width of this slit. And it's related by this formula here. N lambda equals d sine theta. Now this is a very important formula. Lambda is your wavelength in meters. D is your slit width in meters, and N is the order of maxima. I'll explain what that means in a minute. And you know that theta is just this angle there shown. Now the values of lambda, d, and theta will either be given to you in the question, they can be measured in real life, or the question will ask you to calculate them. So we don't really need to worry about what those mean. This n value, however, is the order of maxima. And what that means is simply, well, this central maxima has an order of 0. This maxima here is an order of 1. And this one here is 2. It just means which maxima is it relative to the center. So you can just see that this one here will be 1, this one here will be 2. So if I wanted to work out this angle here, theta, if I'm given the value of lambda and d, well then sine theta would be equal to n lambda over d. And in this case, for this maxima, n will be 1. And for the second order, n will be 2. So it's really not that hard. Now sometimes they may not give you this theta value, but what instead they'll give you is the distance from this slit to the screen, and they'll call this distance maybe capital D. And they might give you this value of the distance between one maxima and another, and it'll be, let's say, x. Now if they ask you to, let's say, calculate the wavelength, and you're given the slit width, well, in this case, you can work out theta because in this case, tan theta is simply equal to x over d. And you can work that out using simple trigonometry. And then you can calculate the sine theta and plug it into the formula to work out lambda. Now, one kind of analytic question they might ask in your question is, well, state and explain what will happen to the diffraction pattern if the value of lambda increases. Let's say you set up this diffraction pattern with blue light, and then all you're doing is replacing that blue light with a red light, and red is of longer wavelength than blue light. What changes in this pattern will you see? Now for a constant slit width, we can see that if lambda increases, for each value of n, this sine theta value will also increase. So what that means is each maxima will get broader. And what that just means is that this wave pattern is just going to stretch out a bit. And what you will also notice is that the intensity of each peak decreases. And this is all because sine theta is directly proportional to lambda. So let me show you a visual representation of what it might actually look like. Here's the pattern that you might have seen beforehand. So for lambda is shorter. Now for a longer wavelength, you may see something that looks like this. You can see that these maxima have now spread out a bit more, but the amplitude of each peak has decreased. And we know that the intensity is directly proportional to the amplitude squared. So what that means in the physical world is these maxima will be slightly fainter. So now let's look at what happens when we change the slit width. So let's say we increase the slit width. So let's say we're going to keep the wavelength constant. If we increase the slit width, well then we can see that this value of sine theta is going to have to decrease for each value of n. So what that means is the maxima will get narrower. And in doing so, it means that the intensity of each maxima will decrease. And this is because sine theta is inversely proportional to the slit width. Now we've looked at the patterns and the effects that occur from diffraction through a single slit. Let's now talk about the effects that occur when we have a double slit instead. We now have a coherent source coming from this red light. As these waves pass through both slits, you're going to see diffraction occurring from both of them. And what's going to happen is these two sets of waves are going to interfere with each other to produce a pattern. Now, if you put a screen, what you're going to see are a series of alternating brighter and dark fringes. And what this means is if this is a dark fringe, these are the minimum. You're going to see alternating bright and dark spots. And this is because the waves will diffract from both slits and superimpose. And once again, when they meet in phase, they constructively interfere. And when they meet in antiphase, they destructively interfere. Now for a double slit, the equation is Ws is equal to lambda d. Now, here W stands for the fringe width, i.e. the separation between two fringes. And this is given in meters. S is your slit separation in meters. Lambda is your wavelength, once again in meters, and d is your distance between the double slit and the screen in meters. So let's label these on the diagram. Well, a slit separation is simply this distance here, the distance between both slits. And in most questions, you're either going to be given it or you're going to be asked to derive it. So you won't actually have to measure it on a piece of paper or something. Your fringe width is going to be this distance here. It's the distance between two equal points, either from one maxima to another maxima, or from one minima to another minima. Your distance between the slit and the screen is simply this distance there, and the wavelength is given by the light that you're using. Now in your practicals, if you were to try and measure the fringe width, W in the equation, what you should do is measure the total length of a series of fringes and then divide by the number of fringes that you have measured. And this will give you a more accurate answer for your fringe width. So let's look at a type of question again where let's say we change one of the variables. Let's say we increase the slit separation S. But we know if we rearrange this, we get W is equal to lambda d over S. So W is inversely proportional to S. So if we increase S, the fringe width is going to decrease. So what this means is you will see more bright and dark fringes in a given space on your screen. And it also means that the fringe width is obviously narrower. Now let's look at what happens when you have white light passing through a single slit. So white light is made up of every single wavelength of visible light. So that means that white light constitutes of the mixture of all the colors going from red to blue or violet. All the colors in the rainbow basically. So just like with other diffraction patterns, you're going to see a very large bright central maxima, With white light, you're going to see a white central maxima. This maxima is formed is because the light actually bends around the slit. It doesn't go through the slit, it bends around it. Now, as I said before, white light constitutes of all the different colors of wavelengths. And remember, for our equation for single slit, we have n lambda equals d sine theta. White light constitutes of a various range of lambda values. So red light has a longer wavelength and violet light has a shorter wavelength. As you can see, if we increase the value of lambda, we're going to see a larger angle because lambda is directly proportional to sine theta. So what you're going to see is for every maxima x other than the central one, red light is going to be found furthest away and violet light is going to be found closer to the middle. And what you're actually going to see is a rainbow pattern being formed at each of the maxima. So you can see that the colors of light that have longer wavelengths are going to be found further away from the central maxima. As you can see that this angle here is bigger than that angle there. So that's why at every maxima, other than the central maxima, you're going to find rainbow patterns. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.